Hello, my name is Alexander Kozlov. I am CTO at CloudBEAR. CloudBEAR is a RISC-V processor IP provider. And in this presentation, I will give you overview about our IP portfolio. CloudBEAR IP portfolio divided into 3 product line series. First is BM series, which targets small and efficient MCU cores. It's represented by 2 cores, BM310 32-bit microcontroller core, and its 64-bit version called BM610. Second is BR series, which are fast and compact embedded cores. When I say fast, I mean cores which can be clocked above 1 GHz and modern technology nodes. BR series includes 2 cores at the moment. Both are dual issue, and one is 32-bit BR351, and another one is 64-bit BR651. These cores are embedded cores for high-performance control, acceleration, and offloading functions. And what is shown at the bottom of the slide is BI series, Linux-capable machines ranging from IoT-level core BI350 to high-performance out-of-order core BI671, and what is shown in the middle, power-efficient dual-issue BI651. I will go through this series and provide overview and use cases, how these cores could be applied in different applications. Let's start with BM series. We have 2 cores in BM series. Actually, it is almost the same core from RTL perspective because implementation uses the same code base. Our cores based on the system Verilog and follow traditional AD flow. And you can switch between 32 and 64-bit versions by only changing a single parameter. It is a 2 to 3 stage configurable pipeline single issue core featuring multiple RISC-V extensions. It is measure core, which is silicon proven at the customer site. It is highly configurable, so you will be able to select and configure not only extensions which you need, but also pipeline, performance features, memory interfaces. You can configure memory subsystem in terms of tightly coupled memories and instruction caches. And you are free to select interrupt controlling schemes. We have several one, we support several one, and debugging features are also available. Based on your need, you can enable standard debug or optionally trace. For your reference, traditional Drystone and Cormac benchmarks numbers are given at this slide. Note that we don't use any proprietary extensions to improve performance, so it's a pure RISC-V compliant cores, and this performance are achieved by standard extensions. Also, we show here a new popular benchmark called mbench IT, which in contrast the synthetic Drystone and Cormac consist of real programs used in IoT applications. The score value of this benchmark shows how much times your core is faster than reference machine, which is ARM Cortex M4. Means BM310 is 19% faster than ARM Cortex M4, and BM610 is 34% faster. As IP company, we already faces this some types of applications in which our customers are using such CPUs. Initial customers looking at the deeply embedded cases, for example, for control path in processing pipelines, such as networking, wireless baseband video pipelines, use them to control some accelerators like AI accelerators. For such configurations, typically customers select basic configurations as limited feature set like RVIC or RV32 IMC, and that's pretty much enough to do that, to control the accelerators. But in some cases, we saw that core or couple of cores not only, I would say, I would call it do state machine-like job, but also runs complex management software like in SSD controllers, wireless, FiMac processing chains, or wearable devices. In these cases, more featured configurations are useful, and customers like to select to include atomic extensions to speed up critical sections in real-time operation systems and simplify inter-core communications. B extension also useful, which until now still in a draft state in the standard, but we support in CloudBEAR it in our hardware, in course, and software tools. Also, N extension increase your speed to process interrupts by reducing the latency and taking interrupts directly in the user mode. And to speed up control code execution, you also likely want to enable dynamic branch prediction, which is available as an optional feature of this course. In deeply embedded cases, chip users usually don't see core from outside world, but we already get case where microcontroller is visible to end user and fully programmable. Our public customer Melander has built a low power MCU chip for smart metering applications based on BM310. In first generation of smart metering devices, they were using ARM Cortex-M0, but in new generation, what customer cares are to improve performance, make performance better even than Cortex-M4 at lower power, to fulfill their requirements for high precision current and voltage measurements. Also, our customer want to reduce the royalty fees since he goes for high volume and want to reduce unit price. And as well differentiate their product by their own IP like security and crypto IP. The engineering samples of this chip is already available, and soon I believe we will show some demonstrations based on it. As for 64-bit version applications provided, which provided by BM610, this core is ideal for management and housekeeping work in large system on chips. It can address full SoC address space, control power, manage security boot, and implement crypto algorithms with the help of B extension. And as you know, the crypto algorithms are heavily rely on bit manipulation and in case of RISC-V on a B extension. Another product series is BR series. It is also embedded cores like BM, but target higher performance than BM series. We have 2 cores available in this series, 32 and 64-bit. Again, like in BM series case, it shares mostly the same code base. These cores are 9-stage dual issue cores, which can be clocked up to 1.2 gigahertz at 28 nanometer worst condition of silicon. As well as for BM series, we support all standard features like branch prediction, physical memory protection, hardware triggers, and configurable interface, input-output interfaces of the core. For your reference, performance numbers of Drystone and CoreMark benchmarks are given here, which are quite competitive. If you need more performance comparing to BM series, you better use these cores. There are many examples of such cores, but I prefer to give you cases, to give you overview of cases which already saw at customer side. We have a customer building industrial automation SoC. At this application, customer needs more performance since quite intensive networking workloads should be performed by CPUs. In this case, one core is taking care of industrial network protocols, while another take care of application itself. In industrial SoC, there are security concerns. So customer want to enable physical memory protection to isolate networking, crypto, and application processes. And as well as low latency is a concern. So then customer enable an extension, which give you capability to handle interrupt in the user mode directly, by which means we can reduce latency of interrupt processing. And as well, we can reduce latency by providing access to the TCM memories directly to the external masters via front port. We're able in this case to place Ethernet packets directly into coarse TCM memories for further processing. To execute code directly from embedded flash, instruction caches with prefetch engines which were used. It helps to execute in place and reduce overall memory footprint of the chip. Of course, these 2 cores should do work together in the system, and we support standard intercore communication mechanisms which are easier to implement in software by providing atomic operations. Atomic operations could be executed not only in the core's local TCM memories, but also in neighbor core TCMs, which allow to implement any synchronization mechanism. Another use case for BR cores, which we face in our work, is kind of a line programmable accelerator. For instance, for video or networking processing chains. Core is placed in the middle of processing pipeline, and provide programmable engine at speeds of 1.2 gigahertz. For such scenario, core can process the data, but also control the data path, and also control the control path. So control accelerators and do some data work. Last series which I would like to show you today is BI series, which are Linux capable processors. We have 3 cores available in this product line, starting from small BI350 to provide Linux functions for IoT devices. This core focuses on tiny area footprint. Second core is BI651, which is dual issue, power efficient core, competitor of ARM Cortex-A53. And last core is BI671, which is out of order mid-range application CPU, providing even more performance. BI350 is tiny core, which focus on pure providing the Linux capability in IoT SoCs. It is very configurable in terms of memory subsystem and overall parameters, so you can reduce the cache line sizes, select cache sizes, the narrow interfaces, and you can set all the things to minimum to make the area of your IoT SoC as small as possible, but in the same time still provide the Linux capability. The i651 is another core. It's more high performance core. It is power efficient in order dual issue core, considered as the replacement of ARM Cortex A53 solution. Here we show the benchmarks of well-known benchmark called SPEC 2006, which not only show your pipeline performance, but also memory subsystem, which is important for Linux-capable cores. As you can see at this slide, we provide best performance comparing to cores like Sci5 U74 and ARM Cortex A53. But if you need to go on more level of performance, the i671 could provide this. We still keep this core not so aggressive in terms of out-of-order structures, which is used to keep power consumptions low. But in the same time, we achieve 75 to 80% of performance of newest announced core, for example, Sci5 U84. But we're still in this case implementing two-way superscalar machine, comparing to that other implementation are using four-way superscalar designs, which allow us to reduce the area and having less power while still provide quite high level of performance. And as you can see, it can give you 1.5 to 1.8 times faster than Cortex A53. And in many scenarios, dual core configuration of the i671 could replace quad core configuration of Cortex A53 with better area efficiency and less power. To give you overview of what is the difference in terms of area and performance comparing to in-order and out-of-order machines. If you compare BI671 with in-order BI651, it is only increased area of the core by 13%. Even more if you look at the dual core configuration with integrated 1 megabyte layer 2 cache, it's only 7% difference. While out-of-order nature of BI671 allowed to achieve more than 50% performance improvement. With small area increasing, you can have much better performance. Especially we saw really good improvements at the memory throughput, because core out-of-order machine can compensate latencies of the memory. And we saw at the memory benchmarks which we have run on this core, 80 to 90% improvement of performance. What is common for all cores in BI series, they could be combined into multi-core cluster. We support full hardware coherency for such configuration. And as well, we support coherency control with external devices. We have a high performance memory subsystem. We implemented fully non-blocking layer 1, layer 2 caches, means cores continue to execute the instructions even cache miss occurs or several misses occurs until, of course, some instruction depends on the load data. To enable this feature, we support multiple outstanding requests in layer 1, layer 2 caches with auto-folder completions. The sizes of request buffers in layer 1, layer 2 is also configurable, so you can tune them according to your latencies in your memory subsystem. To simplify integration in mid and small size SoCs, we implemented a lightweight coherency control mechanism. So if you connect peripheral device or accelerator, you could use at system level, you can use coherent interconnect, that's allowed, but for some scenarios, it's quite heavy, so you better use another option which we provide. It's a coherency controller. So you can connect your accelerator or peripheral devices to the front port of core complex. And coherency controller will take care about layer 1, layer 2 caches coherency with accelerator. So how it works, a coherency controller will snoop layer 1 and layer 2 caches automatically to get most recent modified data and provide it back to accelerator. So that's almost all about overview of our product line. Please visit our website to get more information. And yeah, join us at Twitter where you can check out some videos, demonstration, and latest news. So thank you for your attention. Bye-bye.